my name is Sandrine Heitz. I'm the co-director of the London Centre for Nanotechnology here at Imperial College London. It's really my great pleasure to welcome our special guest today, Sergei Kalinin, who is joining us from Oak Ridge National Lab, where he is a corporate fellow and a group leader at the Center for Nanophase Material Sciences. So very much within the LCN remit. He's received his master's degree from Moscow State University, and then went to University of Pennsylvania, where he got his PhD with Dawn Bonnell, who I think a few of us at the LCN are collaborating with as well. He's co-authored a staggering 650 numbers of papers, has got a H-index of 98, and also received many awards, including the Blavatnik Award for Physical Sciences, the RMS Medal for Scanning Probe Microscopy, and various early career awards as well. He's an expert on a range of microscopies, electron microscopy, scanning probe microscopy, and also I think more recently looking at AI and machine learning. So it's really great to hear your talk today. Thank you also to Shelley for Shelley Conroy for making the link, and we're very pleased to have you at this LCN seminar series, and the floor is yours. Thank you so much.
Thank you very much for the introduction and for the invitation. So just to make sure you can see my screen, correct?
Yes, we can see your screen, and we can see your pointer as well. Thank you.
Super. So basically, I really appreciate your invitation and opportunities to talk about some of the application of machine learning for electron microscopy, with the idea of using it as a tool for both learning physics and extending it towards the automated experiment. So if I'm not mistaken, about 25 years ago, Professor Brown mentioned that maybe electron microscope would be a synchrotron of the future. And when it comes to the instrumentation, the results that electron microscopes can produce now are truly staggering. So the question becomes, how do we transform the measurements into the scientific insights? And this is the area that interested me over the last 10, 15 years. So this is something that I, with the set of colleagues at Oak Ridge, have actively explored. So some of them are coming from the scanning probe microscopy field, and then went of the dark side of doing machine learning. Some of them you know very well as the electron microscopists, but it's a very, very interdisciplinary field. So let me start from the very beginning and illustrate what is that we'll want to do when we are doing science in general. And as all of you know, science starts with asking fairly basic questions. For example, is the material ferroelectric, or is the material superconductive? And the answer to this question goes through measurement. We take a chunk of material, we go to the lab, we collect the electrodes, we cool it, we perform the measurement, and the answer is there. But then we start to ask slightly more subtle questions. For example, what makes material ferroelectric or superconductive? That leads us to the generalization, why is it ferroelectric? So what are the underpinning atomistic mechanisms that they realize between the atoms that give rise to these functionalities? And if we understand the basic physical mechanism, we can start answering the counterfactual question. For example, will the material be ferroelectric if I dope it with some specific material, or if I apply pressure? And obviously, being able to answer these questions, that's ultimately what is material discovery is all about. And then, of course, very often you need to go back into the realm of real materials and answer questions, what can I do to make material practically? The question becomes, can machine learning help us? And there is a very famous statement by Freeman Dyson that new directions in science are launched by tools much more often than by concepts. And machine learning has been a concept starting from 50s, so there were several ups and downs, but it practically became a tool that we as experimentalists can use only for the last decade, probably no more than that. So Another sort of my interest for combination of electron microscopy and machine learning stems from this diagram where sort of we made jointly with India, which shows how the electron microscopy developed over the last 2 decades. So I actually get to Oak Ridge in 2002 when Steve Panicook and his group were happily installing the first aberration corrector on the 601 and 503 machines. And for about 10 years after that, aberration correction was limited to a relatively small number of labs. But for more than a decade, it basically became the biggest growing area in science. And of course, many of you know these accomplishments much better than I would, but it would be sufficient to say that by now, electron microscopy offers the range of capabilities which actually mind-boggling. So as a person who did STM for quite a while, for me, it is really impressive that the wave function of the electron beam can be tuned to impart the orbital momentum. This is really staggering. The fact that you can use the 60 kilo electron volt electron beam to measure the milli electron volt excitations, such as plasmons or even phonons, that's also really amazing. So there are a lot of developments of this, and obviously UK is the place where quite a lot of the leading electron microscopy research is being done. So in US, there are several centers, including Cornell, Berkeley, Irvine, Oak Ridge, and so on and so forth. But one thing that seems to be very common is that there is a tremendous advances in the instrumentation, and which basically realizes the tremendous opportunity to start to learn physics from the data that comes from these instruments. So as it happens, my original background is scanning probe microscopy, and we started to apply machine learning methods in scanning probe microscopy fairly early on. And for about last 5 years, we realized that there is a tremendous potential combining the machine learning methods and electron microscopy. Now, combination is great, but of course it is all about what is that you want to learn. So what is the material or physics problem? And for me, the most exciting problem is what we call the solid problem, meaning trying to understand the structure and functionality of the non-crystalline materials. So here the idea is that obviously condensed matter physics is probably one of the most successful sciences. And partially it is successful because the chemical space, meaning the description of the material structure, is heavily degenerate. So very often we can describe materials through symmetry, concentration, order parameters, thermodynamic potentials. And many of these characteristics can be studied using the scattering techniques. So when you study the X-ray or neutron scattering on the macroscopic object, you implicitly assume that one unit cell is pretty much the same as all the others one. So it's an assumption of the ideal translational symmetry. The problem is that the really interesting materials, such as ferroelectric relaxers or morphotropic materials or Kitaev materials, they're really not like that. So if we take a piece of the relaxer ferroelectric material, put it under the electron microscope, and then make a map where we show the unit volume of each unit cell by color, you can see that there is a beautiful patterns, but the material is neither crystalline nor non-crystalline. It clearly has some correlations and order in the ground state, but there is no long-term translational symmetry. So the question becomes, can we describe the structure of the materials beyond the symmetry-based methods, essentially from the electron microscopy data? And then if we start to describe the structure, we can as well go to things like establishing structure-property relationships and so on and so forth. The question becomes, can machine learning help us? So microscopes allow us to collect the data. Can machine learning help us to make sense out of the data? And here, the situation is actually very interesting because we all know that the last decade has experienced an explosive growth of machine learning methods from areas ranging from computer vision to medicine to autonomous systems and games. But it's very interesting to know that the impact in experimental physical sciences for the time being has been minimal. So, and perhaps that's understandable because if you look at the roadmap of the deep learning, the first big wave of deep learning came less than 10 years ago. It was 2012. Many techniques like GANs or variation layout encoders appeared in 2014. And even the last 3 or 4 years was the constant slew of innovations such as attention mechanisms, transformers, graph neural networks. All of you have seen AlphaFold and mu0, which came out last year. So the field is very dynamically developing. And the question becomes, why is it difficult to apply machine learning in physics? The answer is that first and foremost, it requires domain expertise and domain-specific goal. So if you want to do something using the machine learning as a tool, my advice would be first do it without machine learning, and only then try to identify what are the bottlenecks that machine learning can address. It's really not a silver bullet that can do everything. Secondly, there is a deep disjunction between how the domain scientists think and how the machine learning works. So domain sciences are usually deeply causal and hypothesis driven. We typically know quite a lot about the system that we want to study. And when we discover something, we put one or several new facts in the context of the prior knowledge. That's not how vast
Sorry,
majority of machine learning tools work.
machine learning for scanning.
Say it again. Okay.
Sorry, I wasn't speaking to you. Sorry about that.
Okay, sorry. So, but then there are other differences. So in some sense, you can say that machine learning is not a single answer. It's a culture. It's not a method. And it's a culture that is deeply rooted on the infrastructure. So if we don't have internet, for example, or computers, we, of course, cannot have machine learning culture. But it also results on things like open code and open data. And this is not an easy transformation. A lot of scientific communities start with the idea that you need to keep your data proprietary and you need to keep the code for yourself. And at some level of maturity, they realize that collaboration is better than competition. So in some communities like genomics, this transition happened about 30 years ago. In others, like astronomy or mass spectrometry, it happened not that long ago, but eventually this transformation happens. So with this in hand, the question becomes, how can machine learning help us? And the easiest, at least philosophically, example of machine learning is the supervised learning, when we know exactly what we are looking for, and we essentially use the machine learning methods in order to automate the work as a human. So in some sense, it's not even a science, it's almost like an engineering. So for me, this interest started with kind of many of you have seen the examples like this. When you look at the two-dimensional material in the electron microscope, and of course you see atoms, and then if you keep looking at the material, you see that material that it start to fall apart. And from the perspective of the pure electron microscopy, this of course is the beam damage. And this is something we want to minimize through the use of compressed sensing or lowering the beam energy and so on and so forth. But we can look at this from slightly different perspectives. So imagine that I'm solid state electrochemist, as kind of is the case for myself. So in this case, I essentially observe a chunk of material on the atomic level. So I see where all the atoms are. Almost by magic, I remove the sulfur atoms, and then the remaining molybdenum-rich phase start to form the extended defects. So you see some of them here, and it forms the second phase. So basically, I essentially observe the solid state reaction on the atomic level, which immediately tells me that I should be able to learn how the nucleation happens, how the phase transformation fronts propagate, and so on and so forth. I can look at the same system from the perspective of a physicist. So I observe the multiple entities, and I know that primarily I detect the atomic nuclei. They interact through the set of the force fields. And then the question I can ask is, can I observe the evolution of the system and learn the force fields acting between the atomic entities? So all this information is contained in the movies. The question is, can I extract it? And if I do, how much can I trust it? Of course, I can ask more interesting questions. For example, here, the removal of the sulfur atom happened randomly because I was just scanning the field of view. And then the question becomes, can I remove the atoms that I want? So use the electron beam in order to shape the matter? And in doing so, can I drive the system to evolve to the final state that I want? So rather than having rather ugly looking blobs throughout the image, can I, for example, remove the sulfur atoms in such a way that these second phases start to form the letters O and L rather than something else? And the pathway to answering all these questions start with the purely engineering challenges. And the first of these challenges is that I should be able to take the data stream coming from the microscope and convert it to something that is physical, for example, atomic coordinates and identities. It turns out that this is exactly the type of tasks where the deep learning works. So I can take a neural network, I can train it on the data, and then I can take a data stream coming from the microscope. So this is a graphene. You can barely see the carbon atoms. So this is a hole. The bright blobs are the silicon atoms. So I can take this data stream and send it through the deep convolutional network. And lo and behold, I start to see the carbon atoms as the red blobs and the silicon atoms as the green blobs. So this is not a scientific challenge. This is an engineering challenge, but that's exactly the type of challenges that deep learning can address remarkably well. And of course, we can extend it. For example, I can train the network to find only point defects, but not anything else. And then I have a defect sniffer that finds the defects and automatically classifies it. Of course, it cannot tell me what these defects are, but by looking at them, I can identify what the defect class is, and basically I can decode the point defect reactions inside these objects. But then the question becomes, okay, for the time being, I have found only the things that I expected. I have a reasonably good idea of what the point defects in MOS2 are, because a lot of people studied it before me. So the question becomes, can I use machine learning to understand things that I haven't seen before? So here is a little bit difficult situation, because typically we think about the description of the images using the language of the macroscopic physics. However, classical descriptors like symmetry, they cannot really be defined rigorously on the local level. They can be defined only in some Bayesian sense. So, however, we can still argue that they do exist. I mean, this is what physics is all about. And we can also argue that they are simple, if not necessarily known. And then we can extend this concept a little bit further and say that maybe even if whatever the local structures are, their collective behaviors can be very complicated. So this is all the science about the emergent behaviors, complexities, and so on and so forth. However, the rules that guide the emergence can be expected to be spatially uniform and simple, if not necessarily known. And then the question becomes, can we find these local descriptors from microscopy data? And can we find the rules that guide the emergence of the local structures from the microscopy data as well? And interestingly enough, machine learning can help. But in this case, we need to be very careful about what machine learning tools we are using, because if I use the classical deep convolutional networks, they essentially rely on the premise of continuous translational symmetry. So if I want to find a cat in the image, it really doesn't matter whether the cat is in this part of the image or this part of the image. So I assume that there is a continuous translational symmetry, which allows the cat discovery to be equivariant. That is not necessarily the best approach for atomically resolved images, because we know that on the atomic level, the materials are discrete. Of course, I can go to the different regime. I can say that, look, all I care about is finding the atoms and then analyze the atomic bonding network. That will work, but we also know that in experiment, we have a lot of signal that can not be just reduced to the atomic coordinates. So for example, if I look at the perovskite, the column shape tells me something about the tilts in the z direction. And of course, it also tells me something about the aberrations in my microscope. So I need to somehow combine these two. And the natural way to analyze the material is using the image patches, which are centered on atoms, but contain the information from the raw images. And then the question becomes, what can I do with them? So how would I simplify and find the relevant traits in the data? And here comes a very powerful machine learning method called the autoencoders. When we basically take a stack of data try to reduce it to the small number of latent variables, and then expand it back to the original data. So it sounds very strange. Why would you transform the data into itself? But it turns out that in doing so, you basically reject all the spurious traits in data and preserve only the traits that are relevant. So the favorite example for machine learning is the so-called MNIST database, the 60,000 handwritten digits. So if I take the handwritten digits and compress it just down to two variables, you can see that they sort of form groups. For example, zeros would be here in this latent space, ones would be here, sevens would be here. There is an inverse operation. So here you see what happens if I take the data and compress it to two latent variables. I can also take two latent variables and expand it back to the original data. And then you see the latent space representation. Again, you see that zeros are here, ones are here. The really powerful aspect of the autoencoders is that they can disentangle the representations of the data. So in the quantum science, there is an entanglement. In machine learning, there is a disentanglement. So there is no rigorous definition for it, at least as of last half year, there was none. But it's very easy to illustrate. So if I use the autoencoder on the data along with the classes, you can see that in the latent space, all the sixes, all the sevens, all the eights, they have an order. So they're all chubby on the left, they are all thin on the right, and they're tilted to the left on the top and tilted to the right on the bottom. So interestingly, this latent representation turned out to separate the relevant traits in data, where one of the traits is the width of the stroke, and another one is the tilt. So obviously, there are much more complex examples. So if you know these TikTok apps where show you how you would look like if you were bald, or if you were wearing mustache, or if you were 10 years older, the principle is exactly the same. You find yourself in the latent space, and then you shift in the direction that is responsible for baldness or for having a mustache. But these are great. But now imagine if we apply something like this for the electron microscopy data. We have multiple images of the system or multiple patches in the same image, and then we try to find out what is that they show. Problem, of course, is that the conventional networks are not sufficient to do that, because usually neural networks don't deal with the rotations very well. So we had to build up upon the normal concept to allow for separation of some known variables like rotations or tilts into the separate latent variables. So now our autoencoder will find any object independent on how it is rotated within the image plane. And of course, there is a lot of flexibility to add physics and so on and so forth. But this is how it looks. So what you see here is the evolution of the latent space of the autoencoder. This is how it learns to identify atomic structures. So, and this is the example of another movie of the graphene, which evolves under the action of the electron beam, where we found all the carbon atoms, and we send it through the autoencoder, and we color the carbon atom by the value of the latent variable. You can see that, lo and behold, if the graphene is in the ideal state, so there is no broken bonds, the latent variable is high, and if you deal with the defects or the edges, the latent variable is low. So effectively, we found another parameter that describes the graphene structure, which was already very interesting. Of course, we don't know how this other parameter relates to energy, so we don't necessarily can make a Landau expansion in terms of it, but at least we can describe the structure in the compact form. And then we asked ourselves a very interesting question. What will happen if, rather than trying to find a reduced description, we will also try to force the autoencoder to represent the data in the best way? And then, in some sense, sort of miracle happened. So what happens is that if we start with the raw observation and use the deep convolutional network to find all the atoms, this is a supervised learning task. The network did the things that humans can do equally well or better, but the network does it in an automated fashion. So there is no discovery here, just an engineering problem. But then if we take our data and send it to the autoencoder, we basically tell it, find the structures that are parsimonious in nature, and you don't know anything about the structures. And then if you look at the latent space of the autoencoder carefully, you can see that it has discovered that the fragments that has perfect sense. So if you know organic chemistry, these are just the possible configuration of carbon atoms. You have ideal graphene, you have the 5-7 defect, you have 2-7-7 defects connected to 5 defects. So this all makes sense. But the important thing is that the machine learning algorithm have discovered them. And we verify this discovery using our intuition. So then we can play more with it. We can see how the structures are organized in the latent space. So what is the relationship between organic chemistry we know and the intrinsic language that the autoencoder discovered? And it works. So what are we going to do with this next? I mean, the next step is, of course, to complement it with the theory. So now we are working with our colleagues on big computers to enable the real-time workflow that take the data from the microscope, convert it to atomic coordinate, and send it to the atomic simulation environment. So all of this can be done in Python. Of course, once you have the molecular simulation, then when it becomes slow. So electron microscope gives us data every second. Simulation takes longer than that, but still it's kind of opens the pathway to do things in real time. Question becomes, can we extend it further? So for example, we used our autoencoders in order to discover the building blocks of the graphene. And of course, we can use it across the board. We can discover the building block in ferroelectrics and so on and so forth. Can we use the same approach to build the structure property relationships? And the answer is it's absolutely doable. For example, one of the very popular methods in electron microscopy now is doing the plasmonic measurements using the EELs. So what we can do is rather than to encode the data and then decode the same data, we can actually encode the feature, for example, the plasmonic spectrum, and decode the structure, or vice versa. So it turns out that it works. And it basically allows us to establish the relationship between the structure and properties. So we can essentially create the algorithm that tells us that for this configuration of particles, these are the plasmonic spectra that would emerge. And that allows us to answer the questions like, what would be the possible plasmonic responses in the given set of nanoparticles? Or what should be the nanoparticle configuration in order to derive the desired plasmonic spectrum? There is a limitation. So again, as I said, machine learning is not a silver bullet, and it's very importantly to realize what the limitations are. And the limitations here are that it's system dependent. So if we do this type of analysis on one set of plasmonic particles, it will of course not work for a different set of plasmonic particles. And it of course requires the pre-acquired training data. But these limitations in terms are rooted in the fundamental fact about the machine learning, which is that correlation is not a causation. Let me show you a very simple example that calls the Simpson paradox, which goes along the lines that, for example, some drugs would be bad for men and women, but are good for people in general. It sounds very counterintuitive. Another example is the relationship between exercise and cholesterol. So we all know that if you have a high cholesterol, exercise can lower it. But this statistical data shows something exactly opposite. So the question is why? The answer is that the why is because there is a confounder. So if we take our data and split it in the age groups, you can see that within each age group, exercise indeed lowers cholesterol. But apparently, the older people are, the higher the cholesterol, and the more they try to exercise to compensate for it. So the combination of these two trends gives rise to this false behavior. So the question is, why am I showing you this? The answer is very simple, because in this case, using a very simple data and very simple machine learning method, meaning the linear regression, we have come up with a physically wrong answer. If we use the much more complex data sets, which have thousands and tens of thousand dimensionalities, and if we use the much more complex deep learning methods, this type of problems don't go anywhere. They're just hidden under the mathematics and the methodology that we don't quite understand. And if you noticed, in the last 2 years, people talk a lot about the things like fairness and explainability in the machine learning. And that's exactly where it comes from, because we cannot trust the correlative methods very often. So the question can be, when can we actually use machine learning in physics? And the answer is that if we know the causal links, machine learning is the right tool. So most application of machine learning methods in theory, I mean, theories generally know what is the cause and what is the effect. They can use machine learning. We can use it if the causal links is known and confounders and observational biases are frozen, so within a limited experiment. But if the causal links are multiple unknown, then there would be dragon. That's the part where, on the one hand, machine learning has to be used very, very carefully and only by properly combining it with physics. And secondly, this is the area that can literally bring us to most interesting discoveries. Let me illustrate some of these concepts. So first of all, what can we do to actually take advantage of machine learning? And the first answer is that we can actually start off with moving from correlation to the generative physical models. So what I mean by that is that look at the astronomy as the example. So astronomers don't get to do any experiments. They look at stars. And then based on the observations of the stars, they try to understand the laws by which the universe formed and developed. So the question becomes, can we do the same thing with the electron microscopy? Can we observe an atoms and by looking at atoms, understand the laws by which the system of atom evolves? So what we tend to call physics of the nanoscale system. And simplest example to do this is, of course, ferroelectric material. So this is just a textbook example of what the ferroelectric phase transition is. So we can have a cubic phase and tetragonal phase. And basically, when we draw a picture like this, vertical scale is obvious. This is energy. And the horizontal scale has this mysterious word configuration coordinate, which basically, or order parameter, or collective variable. But essentially what it means is that all the unit cells behave as the same. This, of course, is not always true. So the way to combine the macroscopic and local behaviors is through this mesoscale Ginzburg-Landau theory, which basically allows you to create a certain order parameter. Ginzburg-Landau theory is very powerful, except that as any mesoscopic theory, it requires boundary conditions. So that's something that needs to come from outside. So the question becomes, can we learn these boundary conditions from the experimental data? And the answer is yes. That's actually where my fascination with electron microscopy as the tool to study nanoscale systems started from. So it turns out that if we observe something like an antiphase boundary in the vacancy order system, or the interface between the ordered and high symmetry phase, we can simply take the analytical solutions from the Ginzburg-Landau theory, which contains some number of unknown parameters, some form of correlation lengths, or some time of screening lengths, and we can just match this solution to the experimental observation. So then we just extract it from the microscopy data, and it is either very difficult or virtually impossible to get it in any other way. This, of course, is not limited to the one-dimensional system. We can do something like this for much more complex objects. For example, the vortices that Ramesh group and the molecular foundry folks have observed. So we can create a model that, for example, includes the ferroflexelectric term. And we can try to use the simple machine learning algorithms to establish the best relationship between the observations and theory, treating our flexelectric tensor as the fitting parameter. So it turns out that there is a specific value that gives us the best theory to experiment fit. So by observing these vortices on the atomic level, we were able to learn the flexelectric coupling strengths inside the material. But there is a limitation. So the limitation is that when we work with this type of systems, we almost never know how much can we trust the answers. And more importantly, we also don't know how well, what kind of microscope do we need to actually get the answer that we want. So we reaccessed this problem about 3 years ago when we started to use the combinatorial libraries to explore the phase transition in the bismuth ferrite. So it's a very famous material. If you have a pure bismuth ferrite, it's ferroelectric rhombohedral material. if you doped it with the samarium, it becomes ferroelectric or thermombic. So we worked with the Professor Takeuchi at UMD, who prepared the sample that has the compositions corresponding to this span of the phase diagram. Then we selected several samples from this composition and looked at it on the stem. So for low concentration pure bismuth ferrite, we have nice ferroelectric domain structures. For samarium doped, it's orthorhombic, there is no polarization. And then we have this weird polarization configurations in between. So let me show you just one example of how we believe we can approach these problems in systematic fashion. For example, of just studying the structure of the ferroelectric domain wall. So the nice thing is that for ferroelectric domain wall in ferroelectric, there are only 3 ways the spins can be arranged. And importantly, we know from theory that goes back to 60s that the structure of the domain wall is strongly related to the nature of the order parameter inside the material. For example, for the second material with the second order phase transition, the domain wall would be simply a hyperbolic tangent. And for the material with the first phase transition, it would be much more complex. If it is a Néel wall, then the wall profile would be yet another functional form. So in this case, it looks like we have the experimental data and we have a theory. And then we can start to ask ourselves a question, can we determine the parameters from the experimental data? And the answer is, of course, we can. We just take the experimental data and fit it from the formula. Subtle question is, how reliable is that? Another question is, can we distinguish the different wall models? So if I have experimental observation, can I fit it by this formula and this formula? And based on the quality of the fit, conclude whether the material has a first or second order phase transition? Of course I can, but then exactly the question is the same. How reliable is that? Then you can ask a third question. So let's assume that I cannot distinguish the 2 wall models. What kind of microscope do we need to get reliable data? Is it something that I need to go to the superstem, or is it something that may appear in 10 years from now if we are very, very lucky? And more subtle question is, does the prior knowledge of material help me answer this type of questions? So for example, if I look at the unknown ferroelectric about which I don't know anything at all, or if I look at the material which is reasonably well understood like barium titanate, does the prior knowledge help me answer this type of questions? So notice that it becomes a little bit weird because essentially I'm asking a question whether knowledge of physics of the material allows you to compensate for the fact that the microscope may be having the lower resolution. And the answer is that actually all this, if we want to learn physics, all these things are related. So there was this very famous statement by Donald Rumsfeld about the knowns and unknowns, which of course is given in the totally different concept. But the important thing is that it basically, in some weird form, says the foundation for the Bayesian theory, that basically says that if we want to learn the theory given the new data, we need to have the prior expertise. For example, we need to know the probability of the theory. We need to have the forward models, so how likely is the data given the theory. And most importantly, we need to have the capacity to put it all together. And the important thing, so why the statement by Rumsfeld is important, is because when we try to solve problems in physics, we very often don't appreciate how much we really know. So for experimentalists, we deal a lot with the unknown knowns. We really know much more that we give ourselves credit for. And part of our difficulties forming teams with the data scientists is because their expertise is exactly opposite. So it turns out that if we kind of try to act upon this philosophical insight, it actually works remarkably well. So let's just imagine I simulate the case where I have some noise level in the system, sort of how well can I measure contrast in the position, and I have some sampling. So if I don't know much about the system, I would be able to learn the physics of the material to separate the first and second order phase transition inside this black region. If I know the physics of material better, for example, I have a much tighter prior knowledge about certain parameters, I would be able to, you see that this black regions become much larger. It maybe doesn't seem that large, but it's an order of magnitude, and the order of magnitude in microscope resolution is not a small thing. There is a price for it. The price for it is that if my knowledge is certain but incorrect, then I cannot do physics at all. So at some point, the experimental evidence will take over, but that may be not enough. Next question is, can this approach be extended beyond the Ginzburg-Landau models? So in Ginzburg-Landau description, we use some kind of mesoscopic order parameter to describe the system, but realistic interactions are atomistic. So and this is how, in a very simplified form, this is how condensed matter physics works. So we start with microscopic models, we calculate macroscopic observables, people take real materials, calculate macroscopic measure macroscopic properties, and then make a comparison on macroscopic level. Only 4 years ago, a paper by Melka in Vector Institute came out, who showed that we can use machine learning to go from microscopic models to macroscopic observable. So that was not long ago. Then interesting question becomes, can machine learning be used to establish the relationship between microscopic models and microscopic observations directly? So in other words, can we take an electron microscopy image and fit it directly to something like Ising model? Turns out that it's possible. So this is an example of the beautiful model system of the doped molybdenum sulfide. So you see that we add rhenium, and we obviously start to have more rhenium atoms, and we also start to induce the phase transition. So we form these diagonal stripes. Turns out that we can take the electron microscopy data and we can calculate the free energy of the solid solution based on the statistics of the rhenium atom distributions. So it turns out that all the variety of the atomic configurations here can be described by a relatively simple pair additive model, which basically generalizes across multiple compositions. And essentially, we learned the thermodynamics of the non-ideal solid solution given the statistics of the atoms. We can actually push it even further because we are not limited to study just thermodynamics. We can also take each atom inside the material, look at the neighborhood, and try to understand the symmetry breaking distortions around the atom. And if you do that, you can see that, let's say the zero-order distortion is just Vagard expansion tensor, doesn't seem to depend on local concentration, but the first-order component shows the splitting. So basically, we use the fact that any macroscopic concentration contains a range of local concentrations, and therefore we can basically study the relationship between the local chemistry and the symmetry breaking, which is actually very cool. But then it brings us the question of the cause and effect. So we know that there are at least two effects that control local symmetry breaking. One is the average electron concentration through the classical Fermi surface nesting, and another is local atomic configurations. And the answer is we actually don't know which one affects symmetry breaking. So macroscopically, we would be able to make a field effect device to separate the two, but in observation sciences only, that's actually very difficult. And that brings me to the point that ultimately the functional form of physical law may be not enough. So if we operate in the thermodynamic equilibrium, so we have an ideal gas law, we know that there is a relationship between the volume and pressure, but we don't know, we cannot separate what is the cause and what is the effect, they're just linked. But if we look at this process, we can say that the pressure change is the cause and volume change is the effect. For this process, the volume change is the cause and the pressure change is the effect. So it turns out that in sufficiently complex materials, we also can come up with alternative hypotheses about what is the cause and what is the effect. For example, in ferroelectrics, we know that cationic disorder will affect the polarization field. So cations basically pin polarization. But we also know that ions can move to compensate for polarization. So there are memory effects in sufficiently in soft ferroelectric ceramics. So the question of the cause and effect seems to be strongly linked to the non-ergodic material system. And I think that this is the area where combination of machine learning and electron microscopy can give us some interesting insights. So in the interest of time, let me skip the part when we try to experiment with that, and just briefly talk about the last topic about, okay, for the time being, I talked only about machine learning applied after the data is acquired. And the question is, can I make microscope autonomous so it actually does some of the physicist work? So the justification for that is obvious. There are a lot of microscopes in the world, and most of the time microscopes sit alone in the dark room and turn knobs. And there are very clear cases of automation, for example, cryo-EM, where a combination of sample prep and the mathematical workflows make a really big difference in biology. So unsurprisingly, so a lot of people are inspired by autonomous cars and so on. There were a lot of proposals to make automated microscopes. There is also the word of warning here. For example, Uber promised the automated car in the year 2017, and that did not happen. So it tells you that the problem can be a little bit more complicated than it will originally think. So then the question becomes, why would we even need to have that autonomous microscope? So let me show an example of the scanning probe microscopy, where I look at the material which have a beautiful ferroelectric domains. And then the question I can ask, what are the interesting places here for spectroscopic studies? So first of all, I use my prior domain knowledge to identify this region as the in-plane domains. And the in-plane domains, I don't expect anything interesting to happen, but it's still a good practice to do the measurements to establish the microscope baseline. Then let's assume I'm interested in the properties of the regions with the dense AC domain structures. Again, I will explore them, but ultimately I expect that properties here and properties here would be roughly the same. And then for whatever reason, I may decide that the interesting behaviors can be in the junctions between the crystallographically incompatible domains. But notice that this is my logic. I combine my own understanding of physics of the system and my own ideas about what is interesting to select the regions for detailed studies. A different person can have a different logic. For example, some of my colleagues can say, look, really interesting phenomena are going to be concentrated on the regions where the domain will have the maximum curvature. So the question is, can we imbue the microscope with the logic and capability to make these decisions and implement them? So important statement is that, to be honest, a lot of automated experiments are possible even without the machine learning. So 2 years ago, we come up with the idea of using the real-time feedback and scanning probe microscopy when we simply scan our material, detect the domain walls, and apply a bias pulse when we cross the domain wall. So this allows us to separate the domain nucleation and domain growth phenomena. So this is something that makes me feel kind of somewhat vexed, because technically this could have been realized 20 years ago. It requires only lock-in amplifier and fast relay. It doesn't require any machine learning. So as I said, a lot of things about automated experiment are a culture more than technical capability. But of course, now we can do it in a more sophisticated fashion. For example, we can find the regions of the material that has a high curvature of the domain wall, and then we can tell our microscope to go from one point to another to measure the, let's say, hysteresis loops only at those locations. So notice that this is also very recent work. But the question becomes that how do we find the unknown? So when I say that I want to perform some action when I detect the domain wall, I rely on the fact that domain wall can be determined with the 100% reliability. If I say that I want to study the properties of the domain wall controlled by curvature or by some other parameter, I define my interest before the experiment, and then my algorithm becomes very, very rigid in terms of the decision making. In fact, it's given all the rules before. Question becomes, can it be used to make decisions during the experiment? So there is a framework for doing it called the Gaussian processing, which basically says that do measurements in several locations, construct some prediction and uncertainty of this prediction, and then choose the place for the next location based on combination of prediction and uncertainty. So that's a very powerful method. And first we thought that, okay, if we have a microscope with engineering control, all we have to do is to take our data set, create some descriptor of interest, put it into this Gaussian processing and make it work. And this is kind of the example of simulated data set where we have the Gaussian process tries to operate on the pre-acquired electron microscopy image. So in principle, it can work, but it works very poorly. This type of algorithms are very, very brittle. And the reason for that is exactly because if we do it this way, we describe what we want to find before we even run the experiment, which basically means that everything that we did not expect becomes a surprise to machine learning algorithm, and they're not very good doing that. Of course, we were persistent, so we also implemented this on the operational scanning probe microscope. So this is no longer simulation. This is the experimental workflow. And you can see that, first of all, I mean, it works, but the results are not particularly good. So it takes a lot of measurements before the predictions start to look as anything remotely reasonable. So it kind of takes quite a while. And secondly, in this particular case, if we compare the ground truth versus the prediction, you can see that we sort of can claim that we captured the main features of the observed phenomena, but realistically, that's not something that we are going to do second time. It simply didn't work well enough to justify all the difficulties. So the solution is that we have to learn while we explore. So we have to use the active learning. And this part works. So we need to do a more complex type of machine learning. We need to combine the deep convolutional networks that recognize objects with the Gaussian processes, which allow us to certify this uncertainty. And basically, the solution was that rather than trying to explore, let's say, structure, we actually need to learn the structure property relationship. So in other words, we choose one location on the sample, train our network to establish the relationship between the structure and spectrum, then make a measurement at the different one, update this relationship, and then we can use physics in order to formulate what is what is that interests us inside the material. So let me show you an example. So the good thing about the neon microscopes is that for the last year, they come with the Swift interfaces, which basically allows us to deploy the Python codes directly on the running microscope. So you no longer need to build a controller. You just kind of deploy the code to run on the microscope. And this is how it works. So we took a two-dimensional material, manganese PS3. So it's kind of relative of graphene or MX2s, but it is considerably less studied. So it forms nice flakes. If we look at EEL's spectrum, we see the bulk plasmon and we see the edge plasmon. So we can define a machine learning algorithm that will do the following thing. It will take a structural image. It will divide it into patches. So, I mean, it's stored in memory. So for each selection location, you can find the patch. It will predict what would be spectrum for a given patch. And then it will start to navigate the sample plane, trying to maximize the intensity of the first peak compared to the second peak. So in other words, we tell our algorithm to try to go and find the regions where the edge plasmons are localized. And it turns out that it works. So what you see here is the experimental workflow. So this is the image, and these are red are the points where the measurements are taken. This image is the acquisition function, which basically is the microscope equivalent of the physicist's attention. And you can see that if we run this algorithm on several flakes, in all cases, we found the edges. So this is, unsurprisingly, edge plasmons are sitting at the edges. What's interesting is that in some cases, our criterion put us in some specific location, like here and here. For some reason, these edges are good, and this edge is not particularly good. Sometimes it's kind of tries to explore around the edge and doesn't really lock on a single location. But basically, it shows that we did realize the physics-based discovery. So there are a lot of things that we don't quite understand yet. And of course, there is a very big flexibility of how you tune your algorithm and how you set your physics criterion, but it works. Interestingly, the same thing can work for something like 4D STEM. So it is a very powerful method to study materials such as twisted graphene and so on and so forth. So we can do the same thing. We can establish the relationship between the image patches and the ronchogram. And then we can explore the system using the either on the pre-acquired data. So we try to explore the system using the center of mass angle as navigation or center of mass magnitude. We can also implement it on the real microscope. So in this case, you can see the movies of the acquisition function on visited project where, or visited points, where here the algorithm decided that this is the interesting region for whatever reason. Here the algorithm decided that, okay, for if we define the experiment in this manner, then it kind of runs away. It found that the interesting behavior in the center of the hole, and for some reason the edges. So, you know, it's the first baby steps, but the whole principle is that it works. So just to summarize, I think that now is a very exciting time when machine learning becomes something that we can use. And we can use it to analyze the data, but we can also use it in order to run the automated experiment. There is sometimes concern that, well, microscopes will become automated, there is nothing for us else to do. That's absolutely not going to happen because, first of all, the data interpretation is done in the general scientific concepts. So the general scientific context is not what machine learning is good at. It's the problem of artificial general intelligence, which is kind of not maybe on the horizon for the time being. Secondly, in order to run the experiment, we rely on the prior knowledge, either in form of trained algorithm, but much more often in terms of rewards. So what is that that's interesting? What is that we know about the material? And realistically, it looks like machine learning would be great, but it's not going to substitute for human. It's going to basically allow us to run the experiment when the slow, high-level decisions are made by humans and fast, low-level decisions are made by AI. So it's kind of going to be a tag teaming the science. So this is just a general summary. So machine learning is great, but it requires domain expertise. And the good thing is that now we can do that. And another thing is that we always consider microscope to be a static tool that just gives images, and we have more than enough difficulty to actually convince it to give us good images at the rate more than several per day. But I think that the situation starts to change. So it becomes more a laboratory, which actually allow us to actively manipulate nature and perform the controlled experiment. Thank you.
Thank you so much, Sergei, for an amazing presentation. It was yeah, really a lot, and I had a lot of questions that you also answered during the presentation. So that was the best kind. But we're out of time, but you know, for people who are on, please ask some questions. We've got one from Aaron, but I will leave it for later. So if anyone is there live, please raise your hand or unmute your mic or write something in. I see Shelley appearing there, maybe.
Yeah. Thank you, Sergei, and thank you also for accepting the invite for the presentation. As Sandrine said, it was very interesting for us. One of the things, so I know we have some of the students also on at the moment, but I guess where to start, you know? So if someone was, let's say, working an experimentalist and they were doing PFM or AFM or SEM or STEM, where would you advise them to start besides getting familiar with Python code? Perhaps libraries or...
So in this case, so there is absolutely no need to repeat the pathway that was already taken in the field. So it definitely worth learning the basic principles, because if they're not understood, you cannot even formulate the problem. But the first thing would be to identify what is that you want to accomplish. For example, okay, I have several images of ferroelectric materials which are not atomically resolved. I want to find the domain walls. So that's one type of problem. Another can be, okay, I have a high quality atomically resolved images. I want to find all the atoms because then I want to construct the polarization fields. So if the problem is identified like this, so at this point, it would be relatively straightforward, because there are already packaged networks like Atom AI by Maxim, which allow to do that with a fairly short amount of training. The more interesting questions are, of course, and again, my advice is to not try to repeat it, because I had experience both within ORNL and outside of ORNL. So the best strategy is to learn a little bit of machine learning by yourself to understand the principle, then use the existing packages workflow. And then if you feel that this is something that you need to move forward, then go on GitHub and find the best state-of-the-art tools that actually fit the problem. Because modern machine learning network engineering becomes very, very sophisticated. And there is also hundreds of realizations of, for example, units. So there is no need to reproduce them. It is highly unlikely that it would be possible to do something that is compared to the state of the art. So you just need to choose the right one. But then the interesting things appear at the point when you want to learn physics. And then it is important to be able to formulate the physical question. For example, let's assume that my order parameter is something that exists, but I don't know what it is. Maybe it's not a polarization. Maybe it is something like twist of the domain of the octahedra or whatever. Can I come up with the algorithm that will find this order parameter in the model system? So always work with the model or dummy data. And then can I apply it to the experimental data set to find something new? Most of the time, the answer would be that it is relatively easy to define the algorithm that works on the model data. And almost always it will start to fail rather miserably on the experimental data set. So for me, the big vision that I had 2 years ago was to take the atomically resolved images of the samarium doped bismuth ferrite across the phase transition, dump all the data in the unsupervised machine learning, and get the idea of how the phase transition actually happens. It turns out that this works great in theory. It really doesn't work in practice, because the small difference in the microscope setting from day 1 to day 2 result in being absolutely not able to compare the data from different days. The differences are small, but it is the small details that we want to explore. So we found a way to the another problem is that the same image can have slightly different mistilt in the different part of the image, which basically means that you deal with the polarization changes which are sharp, and some distortion of the way how the atom looks, which are small. So I didn't know any of that 2 years ago. So the fact that I know it now suggests that it was a lot of frustration trying to figure out how to deal with these facts. So for the time being, our solution is to come up with the physically rigid descriptors. So if the physics is fixed, then all the small variations in the experimental setting get absorbed into the sort of essentially thresholding. But we have an idea about how to formulate the problem more broadly, but we don't know how to solve it for the time being. So that's a kind of ended up being the long-term project with a lot of discoveries in the process. But generally, once you define what is that you want to learn, that's always a better approach than just pick some magic silver bullet method and try to apply it.
Yeah. Thank you. I think we had I think probably some of the same problems where you're looking at the symmetry of the stem beam, but we weren't really thinking about the beam spreading after. So the symmetry after and adding those two together.
Yes.
is
Yes.
not as simple as we thought originally.
It's absolutely not simple, and my personal feeling is that there are quite a lot of low-hanging fruit that can be done by combination of machine learning and image analytics. Ideologically, I think we know where it is going to stop, because at some point you simply cannot distinguish what happens inside the materials and the non-ideality in the imaging system. And then the question becomes, how do we try to learn the physics of material better by trying to understand the microscope performance? Because for a physicist, again, it's kind of part of the reason why we started to work with the Bayesian methods, because for example, for the ferroelectric domain walls, the answer was that we cannot distinguish different order parameters given the performance of the existing microscope. So it's sort of trivial answer.
Thank you.
Thanks very much. And any other question from the floor? Otherwise, a quick technical question from Aaron here. So for a particular crystal, knowledge of the structure will reduce the number of possible deformations from symmetry. So that we know from the physics and crystallography, but will ultimately tools such as autoencoders do a better and more general job, I think, regardless of the symmetry? I guess you talked quite a bit about symmetry breaking in those systems. So would it be better to use them?
You see, this all depends on how do you treat your knowledge of symmetry, because it is fairly straightforward to construct the autoencoder that allows for deals with the continuous or the discrete symmetries. So for the discrete symmetries, you can simply augment your data set. For continuous symmetry, that's what rotational autoencoder does. But it is very important to realize that in doing so, you postulate something about the material. If you take the material as the tabula rasa, you cannot postulate that there is any symmetry, because symmetry is the macroscopic construct. If we observe the position of, let's say, 9 atoms in space, we don't know whether the deviation from, say, ideal cubic lattice is because of the noise in the system, or whether this is because the material is non-centrosymmetric. So that's why I say that the concept of symmetry is almost like a concept of the dielectric constant. So they are very well defined on the macroscopic case, and one has to be extraordinarily careful with applying them locally. And the limiting cases are, we postulate that the original phase is high symmetric, and therefore everything that we observe in the microscope is an interesting physical phenomena, but it can be local or it can be non-local and used by something like depolarization fields. So that's the part to be very, very careful about. With the machine learning, we can sort of formulate it as, okay, we postulate that there should be symmetry. Please find what are the building blocks. We can postulate that we don't know anything about the symmetry. Please try to find symmetry and building blocks. Or we can say that, look, we have some uncertainty about the symmetry. Please tell us how would the building blocks look like if we assume that the symmetry most likely is cubic, but can also with a small probability be tetragonal. So then it becomes the probabilistic programming problem. And realistically, most of the things that we deal with the analysis of local data, whether it is electron microscopy or SPM, it's essentially probabilistic programming. We need to find the low dimensional factors that describe the behavior of the high dimensional system. From physics, we know that these factors are order parameters or strain fields, but in experiment, we need to discover them.
Okay, yeah, that makes sense. Okay, great. Thank you very much.